There's some brief information about me. I'm sure you guys have seen it, but I'll go through it just again for the sake of formality. So I'm Ali, also go by Alizishaan. That's the name on my passport, very long, don't bother. I'm originally from India. I was born and raised there in the biggest city, Mumbai. You don't have a lot of people from there here, but that's where I'm from. But I moved to California, and I worked there as a machine learning engineer and an academic researcher. I try to do as much academia as industry permits, but yeah, so that's my interest. And I work at Pivotus Ventures. We're hiring people, by the way. So if you need a job, hit me up after the conference. Here's what I'm going to talk about. Detecting offensive messages using deep learning. This talk is about my experiences while working with the company I'm currently working. So we're basically building a customer service platform, right? And we just realized that what if people are not behaving the way they're supposed to behave? What if they're talking shit, right? And we decided to solve that problem. And that's where this comes from. All right, so again, what the fuck is this? It is a system which prevents people from using language like this. Like, you don't want people to be throwing around the F-bombs. We're living in an age where of offensive content, so racism, sexism, and like Twitter is full of that. Instagram is full of that. Instagram is better off, I would say. Facebook is full of that. And if you look at any post on Facebook, any random post on Facebook of like significance, and if you go to the comment section, you're going to see a pile of shit. All right, you're going to see a ton of bad messages, and companies are taking steps towards addressing it. If you've been following the news, Instagram has deployed an automation to detect offensive content and get rid of it. There's a couple of papers from Yahoo which discuss this topic, and there's been work by multiple other agencies. And just before I flew here, I saw a paper that was published in 2018, which was about the same topic. So this is a hot area of research right now. There's a bunch of papers being published, a bunch of work being done. So what I'm going to do is I'm going to focus on how to do it from an industry perspective. When we're working in industry, let's be honest, we don't give a damn about academia, do we? We very rarely see a couple of papers, but that's where the knowledge comes from. But there's like, if academia gives you the how, like if it tells you the what, gives you the science, we need to build the technology. Right? So this talk is going to be about how do you take the science in parts. I'm going to go through the science in a bit, like in a brief manner, but it's about how you take the science that exists and build the technology around it to use it in a realistic setting. All right, so there have been numerous approaches to tackle offensive content. One of the most primitive, or one of the most basic approaches has been to use something like a word list. So you have a list of words, like say, fuck, shit, bitch, dog, Mexicans, things like that, right? You have a list like that. You have a list like that, and then you just go through the content and just randomly start shooting it out. Like you use regex. Like there'll be a lot of techie system engineers who'll be like, oh yeah, regex can solve all problems. That is the thing with regex. Try using regex, and that's exactly what's going to happen to you. You want to know why? Look, so list-based approaches fail. They're inefficient because they cannot capture the context in which you utter a word. So let's say I use stuff like, that's fucking awesome. Was I offensive? No. But if you try to use a list-based filter, the F word's going to get censored, right? That's why it's a bad idea. Another thing, like if you look at stop word lists on the internet, I have seen multiple lists in which the word Mexican is offensive. I mean, it's bias, it's cultural bias, but that word is offensive. So now if you say something like, I hate Mexican food, that is not an offensive term or not an offensive sentence, but that's going to get flagged wrongly by your classifier because, well, you're using stop words. There is no intelligence involved there, right? But if I say I hate Mexican people, I am being offensive. That, the second one, is offensive. The first one is not. So using a stop word based approach is not going to help you solve that. Number 2, alternate spellings. So if you say, like, you can spell a certain word in multiple ways, and people who are used to social media have seen that, which is most of us. So most of us have seen alternate spellings. Most of us use alternate spellings. So like, if you look at the first example, the word bitch, or in English or in Spanish you would say perra, right? Is that it? Is that what it is? Perra. So now, so the same word now, as you can see, is spelled differently. As B exclamation mark TCH. A human reader is going to know, yeah, he's calling you a bitch. But a system, a stop word based system, is going to fail. Another thing, like many times now, there's this new trend of excluding the vowels. I'm not sure if it exists in Spanish, but in English, people are doing this. So to evade stop word filters, people are doing that. They're literally like writing stuff without the vowels. So now if you use a stop word based filtering approach, you're going to fail here. Number 3, the stop word list cannot be used to classify offensive content that on the basis of the idea. So now you can be offensive but use normal language. The example there, your mom is a fat cow. Tu madre gato, no, tu madre gordo, huh? Vaca gorda. Tu madre una vaca gorda. So now, none of those words by themselves are offensive. But the sentence, the collection as a whole is pretty bad, right? Now, that is going to pass through a stop word filter. Now imagine something like that happening in a customer service setting. An agent telling that to a customer, or a customer telling that to an agent, and vice versa, you know? So that's not very good. Number 2, racist content. So again, I haven't used any bad word, but Muslims deserve to die. You're not going to pick that using a stop word. Let's say you put Muslims in, you can argue that you can put the word Muslim in the stop word list, fine. But let's say Muslims celebrated Eid yesterday. Perfectly correct sentence, but the stop words filter is going to wrongly classify that, which is why it is a problem. Sexist messages. Women belong in the kitchen. You can also extend this approach to other stuff like, say, something that's inappropriate for a given setting. To solve this problem as a whole, what do we need to do? We need to ask ourselves, what do we need to do? A, we need to be able to capture context. So we need to be able to say that we need a system. We basically need an automated system which can be like, all right, this stuff is offensive and this is not. We need something to definitively tell us that this stuff is offensive and not. So what do we need to do for that? We need to capture context. So we need to figure out how if a bad word is used, in what context is it used, right? So this is fucking awesome is fine, but this is fucking terrible is not. We need to be robust to alternate spellings. So like the example that's given there, she's a whore and she's a whore, W-H-0-R-E. Now I don't know what whore means in Spanish. Any helps? Any tips? What? Puta. Narcos, I forgot about that. So let's say you write puta with a U, like the regular puta, and then you write a puta with like a micro sign. It means the same thing, but the classifier or the automated system needs to understand that they're one and the same thing. And then number 3, we need to classify on the basis of the central idea of the text, not the language, right? Not the language being used, but the central idea, like what is this sentence trying to say? What is the message? Is the idea as a whole offensive? So like stuff like Germans are bloody awesome, that's fine. Bloody is a bad word, but Germans are bloody awesome is fine, but Germans are bloody smelly is not so fine. Same thing with Mexicans. I love Mexicans. Mexicans are good people and Mexicans are lazy people. When you say that, when you call them lazy, you're stereotyping, you're being bad to them. So in a nutshell, we need to build an automated system that kind of understands human language. So here's the thing. How can we get a computer to understand human language, right? Now, the conversations are going to be in text. They're going to be in chat. How is a computer going to figure out? Computers are dumb, rule-based machines, right? As fundamentally, a computer is like, it's got no brain of its own. It just follows what we tell it to. As programmers, we write syntax. We're like, if A, then B, if B, then C. That's how it works, right? Fundamentally, on the basis of a fixed set of rules. But the very nature of human language is non-rule based. And even if you were if you were to try to make up rules, you're going to have like 50,000 rules, 60,000 rules. And we know how that goes with, putting those in a computer. Like, imagine trying to code those many rules in a program. It's impractical, right? And those rules change every day. Today there's something trending in social media. Tomorrow there's going to be something else, right? Those rules change all the time. How are we going to account for all of that? So hard coding rules and lists are not a very good way to tackle this problem of detecting offensive content. So what do? We go to what is in trend: deep learning, supervised deep learning. So one of like a pioneering researcher in academia, Andrew Ng, and now in industry, he's been doing a bunch of cool stuff. He gave this analogy. He said deep learning is like a rocket ship, all right? The engine of the rocket is your deep learning model. And the fuel, the gas, is that what you call it? Petrol? What's it called in Spanish? Gasolina. The gasolina is the data. All right? So the data that we have is the gasoline that powers the deep learning engine. What's good about it is you use the data once, you train a model, and you don't need the data anymore. Now, each time you put in entries to that model is going to give you results that you want. All right? So what we're going to do is we're going to focus on the two approaches. A, how do we get the data for our offensive content? How do we work with that data? And then what model do we build on top of that data? So there's two parts to it. There's the content, there's like the data that we're going to use to train. And once we've trained on that data, we get a model. Like, what model are we going to use to train on it? Like, what model are we going to train using that data? And then the next part will be about how do we expose that model to end users? How do we, use it via an API or microservice? You saw it there. Let's go ahead. So before all the fancy stuff begins, let's set some ground understanding, or like a fundamental understanding of what offensive is. For your application, for some applications, a profanity filter would just be fine. So don't use bad language. So you need to pick your data set accordingly. And if needed, build it. It's possible to, so there's like, on this particular application, there's, from what I know of, there's 3 available open source data sets. One is from the NAACL conference, one is from Crowdflower, and there's one on Kaggle. So there's 3 open source data sets available for like sexist, racist content classification, offensive speech, so which is profanity basically. When I say pick your data set, you can also build. So let's say you want to build a classifier which says stuff that's exclusively like sexist or non-sexist, or like, let's say you do not want a particular kind of talk about a particular group. So an example of this would be, you can say like, okay, Germans are fine, Germans are so-and-so, but anything negative, you want that to be flagged. So you can build your own data sets, and there's ways to do it. One of the most popular ways of doing that is to create sentences and then annotate it in a crowdsourced provider like, say, Amazon Mechanical Turk, and there's a bunch of companies doing that as well for you, if you have money to spend. But people are willing to do that. That's the point. So now once we've decided what our data looks like, we need to figure out how are we going to use it, right? We have the data. What are we going to do with the data? Everything is turned to numbers. Our data is a bunch of strings, right? It's just a bunch of strings. It's like, hey, message, offensive or not offensive. That's what we have right now. So now we're going to turn everything into numbers, like everything. So the entries, that is the data, the messages that are being spoken, and the labels, everything will be turned to numbers. Let's figure out how that's done. Sentences are split into words and characters. So like, let's say if I say, this is a test, splitting into words means this is a test, right? And splitting into characters means THIS, space IS, space IS, space A, space TEST. That's what I mean. Do you get it? Do you follow me? Yeah. All right. Now, each word, so this is, each word is represented as a NumPy array of numbers, or a Python list. Don't use lists, they're bad, but use the NumPy array. They will take your memory out. Don't use them. Each character is represented as a binary array of numbers. Again, use arrays, please. List will be overkill. Now, the question is, how do you represent words as numbers, right? A word, this. How can you possibly turn that into a number, right? That's a question I feel will be like, again, it's a string. How do you go from string to a number? Let's see. Deep learning gives you some secret sauce called word embedding models. They turn words. Their job is to take a word, take a goddamn word, and turn it into like a list of numbers. Again, don't use lists, but a list of numbers, right? And these are pre-trained on corporate. Usually these are pre-trained on huge scale corpuses. Popular models are Word2Vec Google, FastText, Facebook, and Glove. I'm pretty sure Google has a Word2Vec for many languages across the world, not just Spanish, but like minority languages. So like languages, like I'm pretty sure they'll probably even have like stuff for Middle Eastern or African languages, which are typically underrepresented in the linguistics, computational linguistics community, but you'll have resources for that as well. So this approach is, the reason I'm mentioning this is because this approach is language agnostic. So it doesn't matter if your classifier is working with English or Chinese or Japanese or Spanish. The fundamental structure is going to remain the same. Maybe not for Chinese, but what?
Yeah, maybe Chinese more apply.
Yeah, maybe not for Chinese, but the fundamental approach is going to remain the same. Also for Chinese, you'd be surprised. And the reason I believe that, and the reason I say that, is because the Google Translate model that works, so Google Translate, everybody knows? Oh wait, Traductor. The Traductor model, the infrastructure behind, you'd be surprised. It is trained, so it's not like you would expect English to Spanish, Spanish to French, French to Mandarin. You would expect them to be trained on different like unique data sets, right? But you'd be surprised to know that the entire model is one. Like entire model, the base model powering all translations between different language pairs is one. So a classifier that has been trained to, convert French to Japanese is the same as the one trained to convert, say, Swahili to Urdu. So these models are pretty robust and pretty interesting. They can do pretty cool stuff. So like, as I say on the slide, these word embedding models have some special properties. Let's see what those are. What these do is, these models do is they represent numbers in a high dimensional space. What that basically means is it represents them as a list of numbers, and words that are closer to each other in meaning are grouped together. So to give you an example, France and Paris are going to be closer to each other than France and, say, drugs. It's a different word. So in vector space, imagine like a two-dimensional space. Do not try to imagine more than that. I can. Nobody can. You can imagine only up to 3. Even 3 is hard. Even most physicists can. So just imagine it in like a two-dimensional space. Like words closer in meaning are closer to each other, and words that are not so close to each other in meaning are further away, right? And these words have interesting mathematical properties. So properties are like in these models, the words have interesting properties. So king plus man minus woman will give you a set of numbers which will be closest in meaning to queen. So those are the cool properties. Now, similarly, so these basically are capturing semantic information. Similarly, you look at France plus Paris minus Colombia equal to Bogota. Why? Take this term here. France plus Paris. What relationship does it give? Capitals, right? Bogota plus Colombia should give you the same. And these equations work. That's the cool thing about word embedding models, right? Now, we've turned words into, somehow we've managed to turn words into numbers. So the next question is, how do we represent characters as numbers? We've got a bunch of characters. We've got A. How are we going to turn it into a set of numbers? Like, how can we possibly do that, right? That's what the baby's wondering. He's like, how the hell do you do that? So we use something called as one-hot vectors. These are basically vectors containing all zeros, right? Let's imagine them this way. They're vectors containing all zeros. And now, if you want to represent a 1, or you want to represent an A, right? Let's say we're trying to represent all the letters of the alphabet to begin with. So if you want to represent an A, you just turn the index of A, so the first value, to 1. Everything else remains 0, right? Similarly, Z or Zeta will be represented here as the last position. The position corresponding to the character is set to 1. Everything else is set to 0, right? Do you understand a little bit? Yes. So the data that we had, the words have been turned into numbers. So what did we initially do? We took a set of words. We took a set of sentences, labeled pairs. We separated them into words, separated the sentences into words and characters, right? The words have been turned into numbers using embedding models, and the characters have been turned into numbers using one-hot vectors. You can also use this one-hot vector technique to convert the labels into vectors. So like offensive will be 0, 1. Non-offensive will be 1, 0, right? So you can do something of that sort with labels if you want to, or you can just leave it and use a regression model instead. Up to you, your call. So now our data is ready. What are we going to do with the data? As we discussed, the rocket is ready. Gasolina is ready. What do we do with the gasolina? Where do we put it to make it work? We put it in the engine, in the rocket engine. The rocket engine here is our model. So let's look at how we're going to build the model, right? So we're going to use something called as convolutional neural networks. Are you guys familiar with it? Or do you want me to go into it in depth? Are you good? You don't want, I saw the previous talk address convolutional neural nets, so I kind of took them out because I didn't want to be repetitive. So we're going to use convolutional neural nets, right? We're going to use a convolutional neural net for words, and we're going to use another one for characters. 2 different nets, and we can add some syntactic sugar in the form of MLP. It'll give you a few points boost in performance, but it's just optional if you want to do it. So let's see how this works. So what I did was, we built the models using Keras, Python and Keras. So this is the Keras library, and each layer is callable. So don't get shocked by this. Each layer can be called, right? So it's that layer that's being called. So we first start with word inputs. Before I go into the code, I'll tell you that the main objective of doing this, so when you perform convolutions over words, the main intuition is to capture semantic information from the words. So like what you're doing by convolution over words is you're looking at words in groups of 2, 3, and 4. Or sorry, 1, 2, and 3 here. All right? So you're looking at them. You can change those numbers. Best performance, whatever works, like whatever gives you best results in R&D. So what you're basically doing is you're looking in a sentence. So like in this is a test, you will be looking at if 1, 2, and 3. So the one convolutional net will be looking at this is a test separately. The 2 combination will be looking at this is a, so on and so forth. So that's what's going on here. And here's the code to do it. It's using Python and Keras. All right. That's the word level embedding. So after the convolutions have been performed, here's pooling. In a nutshell, what pooling does is pooling just extracts the good stuff, or the most relevant inferences from the convolution process, right? That's all you need to know for the purpose of this talk. If you're interested, be sure to look it up in detail later. And I'm also happy to answer you after the talk. But for now, let's say that pooling just summarizes or extracts the best bits of the convolutions. All right. Now, we've used a word level CNN. Now we're going to use a character level CNN. Why are we using a character level CNN? What's the intuition? Now, what we're going to do is we're going to look at characters in groups. So we want to say that, like, our application demands that we need to say that PUTA and P mu microsign TA are the same thing, right? So we need to be able to say, like, we need to be robust to misspellings. So using character level CNNs is going to help us do that. All right. Now, what we do is, again, we perform convolutions using size 3, 4, and 5. So if you guys are familiar with NLP, these are also called as trigrams, quadrigrams, 5 grams, n-grams basically. So this is the performance, or like the function of this convolution is the same as n-grams, right? It's very analogous to n-grams. You can think of it that way. And again, we're pooling here. So we have the layers discussed, blah, 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 blah. And then we're pooling here to extract the best bits out of it. All right. So now we have the word content ready. We've got the character level content ready. What do we do now? We've got 2 nets ready, but we still haven't done anything cool with it. All right. So what we do is this. So here's where the user input comes from. All right. User input comes in. It's split. We've seen the data processing bit, so I'll just skip ahead to the good stuff. So another fine bit of detail before I skip, sorry. Another fine bit of detail, like the word level inputs, you can just load them using pre-available libraries like GenSim. So you can literally, for a word embedding model, you can literally download a file from Google, a pre-trained embedding binary flat text file from Google, and load it using something like GenSim, or there's a bunch of Word2Vec flat file loaders. You could write your own if you want. I would not recommend doing that, but if you want to, go for it. Using some cool generators and stuff, but never mind, that's for later. So one-hot encoding has been performed. One-hot encoding is pretty simple. You just do a dict lookup, set lookup, whatever you want to do, and convert it to an array, not a list. And then you feed it to the word level nets and the word level CNN and this character level CNN separately. There's no intermixing so far, right? Now, let's address this block. We had pooled like the good stuff from word level convolutions. We had a summary, the good stuff or the summary from the character level convolutions. So what we basically do is we place them on top of each other. That's it. We're just concatenating. We're not doing anything more. We're just concatenating. We're concatenating, and then you have a multi-layer perceptron in the front, and here's the code. So there's concatenation going on. There's an additional perceptron if you want to use, and there's labels. All right. Let's go ahead, build and train the model. So like I said, and I'll go a bit fast now because we have little time, we're running short in time, but I'll try to cover as much as I can. We code the model in Python. We use Keras and TensorFlow. And the good thing about Keras is that you can use any other backend. So you can use PyTorch. You can use, if you're like a Microsoft fan, you can use CNTK. You can use Amazon MXNet. Whatever Keras supports, you can use it. I'm not sure though if Keras supports these frameworks, but supports MXNet or CNTK. I think it supports CNTK, but it definitely supports Torch. Label data, again, is divided into training and test sets, the normal performance, and we achieve 96% accuracy on test data using which is the state of the art on the training data. And like we at the research team are super thrilled about it. We're like, oh yeah, problem solved. Like, deal done. We can ship the model as a flat file. We're good, right? And we share that with our business team, and they're like, cool. Let's put it in our product, right? Let's build it up. How hard can it be? The hard stuff has been done. Wrong. Now, when you go to the developers, you give them a flat model JSON file and be like, here, sir, use this. They're going to be worse than that. They'll probably give you offensive content there. But so how do you do that? And you try to give a flat file to a DevOps guy, and they'll be like, how the fuck do we deploy that? So the solution, expose the model via a Dockerized microservice, which is accessible via standard RESTful endpoint. It's self-contained because it's Docker. It's independent of the host environment. That's all the good stuff that comes from Docker. Easy to deploy, easy to scale. Easy end-to-end audits. That's a functionality that we've built into it. It can be extended, like again, this approach can be easily extended to encapsulate any Keras model. So let's say you don't give a shit about detecting offensive content, right? You're like, I don't care. That's not my application. I want to classify images. The same approach, the same software architecture can be modified to fit that. And you have configurable logging, which I feel if you guys have used the logging module in Python, you know what I'm talking about. So why Docker? For these reasons. The benefits of containerization from systems engineering. All build and run dependencies are taken care of. Packaging in a Docker container makes it independent of the host. But since this is deep learning and it's like a cool field and it's fancy and it uses GPUs, there's some tricky stuff involved. Like it's not, I mean, packaging can run into some difficulties that you would not run into normally. But it's pretty robust. If you use CPU inference, it's pretty robust. And even for like GPU inference, you just need to take extra steps. It still works. And if it can run, so like if it can run Docker, it can run the microservice. So if you want to run it on a Windows box, you want to run it on a Linux box, you want to run it on some weird ass OS box, like you can just run it. If you can run Docker, you can run this. Our logging system. So these are the benefits that come via Python. And what you can also do is just pipe your console output to Docker and then handle logging via Docker. So like write to FluentD, write to Datadog, write to Splunk, whatever you want to do. So just you can also let Docker take care of the logging. It works pretty fine. And last thing, log hashes of inputs and outputs. So if you're working with sensitive data, it's wiser to hash it than to like just leave it open, because then if somebody goes to the logs, there can be a privacy breach. Easy audits. So this is the functionality that we built into it. I'll show you the system diagram in a second, so don't worry about it. The goal is to implement end-to-end auditability. So from the time a request comes in to the time it goes out, we need to log everything, like everything that's happened, right? So what we do is, the moment a request comes in, we assign it a UUID, and then once the UUID has been assigned, each module, each submodule, so like the splitter, the word vector, the word-to-vec model, the character one-hot encoder, everything follows that ID and starts and logs it to whatever source you've decided, right? So here's the model. The user input comes in. There's a REST interface, and inputs being split, going to the word embedding model. We've seen all of that stuff before, but the new additions here are the REST interface and the logging module. Yeah, our system is ready.
So I just want to address this concern. The technology and everything is super good, super clear, but notice how this kind of system can influence what happens to the life of one employee or one customer. So when we're about to like plan, deploy and everything, one of these kind of systems, we're gonna need to think about what is gonna happen. So you have like a bunch of agents, and then your system flags one of these agents as have used bad language towards a client. So it's good to think before we start building this. It's good to think what are gonna be the implications. Is this guy gonna receive a memo? Is this guy going to receive a mail from HR, a call from HR? Is it gonna be fired? Is the system gonna be able to explain itself, to explain why did it flag a conversation as used of offensive language? So so coming back to the analogy of that deep learning is a
rocket ship.
Yeah, it's a shuttle. Like these things are super powerful, and they can take you literally out of the world. However, always these things are in the verge of explosion. So you have like an explosion that you could kill you many times underneath your butt, and it's happening.
I mean,
So
what I understand from your question, so there's two questions or two sides to the question that you raised. One, the technology, how reliable is the technology, the reliability of the technology, and two, how can you explain the explainability of technology, right? The consequences are emanating from the reliability of the technology and if it can explain itself. So one, we know that technology is not perfect. Like even on the research table, we had 96% accuracy. So what we do is we engineer business rules around the technology to be like to account for the limitations of the technology. So now we know that the technology A cannot explain itself and 2 is not spot on, right? So what do? We do not send a memo to an employee directly. We send that conversation to the manager, to a human being, let him take a look at it, and then send a memo to the employee. So you have to engineer. So when you're solving a problem, like you also have to, a part of solving the problem is also to engineer the social rules around it. So you're going to have to engineer the social constructs accordingly. Do not send a memo to an employee. And to address your questions about explainability, there's a ton of research going on. There's a paper by Jeffrey Hinton which does that. There's a framework available, if I remember correctly, it's called LIME by FAIR. I'm not sure by whom it is, but this is a framework which lets you explain the predictions of a classifier. So you can actually use that and engineer a system around it. But for the purposes of this conversation, I would just use social engineering rules to ensure that that doesn't happen. Like, just do not automatically fire an employee or give them a memo. Like, do not automate that pipeline because we know our technology is not good enough. You know, it's kind of like guns. We know guns fire, but just don't. Guns and cameras. It's like connecting cameras to guns. So if you see an intruder, shoot. That's basically it. So do not shoot. Do not wire that pipeline. Tell a human there's an intruder, and then get the human to shoot. Right?
Hi. I wanted to ask, like, before the splitter comes in, like, if you were doing like any sort of, I don't know, regular NLP processing, like the tokenization process or some sort of word stemming or lemmatization for the input data. And the second question is, like, I was curious, what would you change in case you need to predict like multiple labels? Like, let's say the probability if the incoming text was like, let's say 50% like toxic or nudity or harmful or like multiple, like multi-class, multi-label stuff.
Got it. So I'll answer question one first. Question one was around using tokenization, lemmatization, and like basically feature engineering, right? There's a ton of literature available out there which supports, like, which says that hard coding or feature engineering and using a vanilla classifier, that is like that's the older generation of systems. That's what older generation systems used to do. Something between filter maps and like something between your lists and deep learning. The thing with tokenization and lemmatization is you won't be able to capture semantic information which is particular to that language. So for a lemmatizer, or for, like, let's say you stem it into smaller parts, right? I'm not sure what stemmers you'd use for Spanish, but for English, let's say you use a Porter stemmer. So it'll give you the root word. Now, how do you get the semantic information that a root word gives? You know, it's harder to represent that, which is why those kind of classifiers are limited in functionality. Number two, you're talking about multi-class classification, right? So the multi-class aspect of it is represented in your training data, of course, and the output layer that I said, where I said one hot encoded output, so offensive or non-offensive, that was a binary classifier, right? So now this time you just take an output over your n classes. So let's say you want nudity, and the property of a softmax is it sums to 1. So if you give something, it's going to give you a distribution which says, all right, this is 40% toxic, 40% hate speech, 40% or 20, whatever the math is. So it'll give you something that adds up to 100%. So you can do multi-class classification that way by just changing the last layer of the model.